6.2 The nature of energy. The wave nature of light does not explain how an object can glow when its temperature increases. Max Planck explained it by assuming that energy comes from packets called quanta. Einstein used this assumption to explain the photoelectric effect. He concluded that energy is proportional to frequency, where h is Planck's constant, 6.626 times 10 to the negative 34th joules second.
We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light impingent on a metal, and the energy of the photoelectrons emitted are shown on the meter at right. If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength and higher energy photons, they may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelength still, higher photon energies, we can see photoelectrons emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path shows photoelectrons emitted at the highest energy. So here's an example of the photoelectric effect. Thanks, Lonnie, for that great demonstration.
Sample exercise 6.3 Energy of a photon. Calculate the energy of one photon of yellow light with a wavelength of 589 nanometers. Our task is to calculate the energy of a photon given its wavelength. We can use equation 6.1 to convert the wavelength to frequency, and then use equation 6.3 to calculate energy. The frequency is calculated from the given wavelength. So we have the speed of light divided by the wavelength. So our frequency is 5.09 times 10 to the 14th hertz. We then multiply the frequency by Planck's constant, 6.626 times 10 to the negative 34th joules second. The seconds will cancel out, and we will be left with 3.37 times 10 to the negative 19th joules of energy. If one photon of radiation if one photon of radiant energy supplies 3.37 times 10 to the negative 19th joules, then 1 mole of these photons will supply 6.02 times 10 to the 23rd photons per mole times 3.37 times 10 to the negative 19th joules per photon, which is 2.03 times 10 to the 5th joules per mole. This is the magnitude of enthalpies of reactions. So radiation can break chemical bonds, producing what are called photochemical reactions. Practice exercise. A laser emits light with a frequency of 4.69 times 10 to the 14th hertz. What is the energy of one photon of the radiation from this laser? If a laser emits a pulse of energy containing 5 times 10 to the 17th photons of this radiation, what is the total energy of that pulse? If the laser emits 1.3 times 10 to the negative 2 joules of energy during a pulse, how many photons are emitted during the pulse? If one knows the wavelength of light, one can calculate the energy in one photon or packet of that light. We have 2 equations now to describe light. We have the speed of light is equal to the wavelength times the frequency. And we also have energy is equal to Planck's constant times frequency.